Hi everybody, it's Luke from Cocos. On the previous video, we successfully used WebGL to draw a triangle on the canvas. This video continues some additions to the content of the previous video by drawing different things. Following knowledge points. 1. How to effectively draw multiple triangles, and 2. How to draw triangles of different colors. Let's start with our first knowledge point, trying to draw a triangle. Now most people will think, I know how to draw a triangle. Can I draw a few more? No problem. Then we'll draw a rectangle as an example by drawing an extra triangle. I'll add one more triangle to the original triangle from our last video. Next, modify the number of vertices in the draw arrays. We'll run it again. And this time we've successfully drawn a rectangle. This is actually not a problem to draw, but some of you who are detailed will notice that the two of our submitted vertex data are duplicates. I originally drew a rectangle in 4 points, but now this one has 6. That will produce about a 50% more overhead. If the scene is very large, the issue will become more and more serious. Therefore, the solution that can be used is to provide an optimal vertex. After that, just specify the order of drawing. We can call the specified method of drawing the vertex index, corresponding to the index buffer object on WebGL index buffer object, also referred to as IBO. How do you understand the IBO? Let's take a look at this picture. First of all, I will delete the 2 vertices that repeat in the second triangle. The remaining 4 vertices mark their array indexes. After I have an index, I can clearly define the true triangles. The first triangle, vertex data, takes the top point index 0, 1, 2. The second triangle, penetration point index 2, 1, 3. Submit data to the WebGL index buffer object. WebGL will be drawn in that index. Please note that the proposed vertex index needs to be submitted in a counterclockwise order. This is because one object usually has 2 faces. One is facing us, and one is visible. It would be a waste of time to draw both, so WebGL will actively eliminate the back side and leave only the front side. This must have a set of rules on the data submission. By default, triangle defined counterclockwise is positive. That is to say, the first triangle is submitted as 0, 2, 1. Then it is possible that the triangle will not be visible. We'll share more about this in a future video. So let's move on. In the previous video, we used the method of GL draw arrays to draw vertices. If a vertex indexing approach is used, we'll instead use gl.drawElements to draw. Next, try to redraw the rectangle with the index buffer object. Let's take a look at these 2 vertices, which I want to eliminate. The vertex order I submitted here is 0, 2, 1, and 2, 3, 1. The order is clockwise, not counterclockwise. But why still draw it like this? Because as I said, the default rejection is the back side, leaving us the front. This is because no open surface is open by default. Culling is enabled by default in Cocos Creator 3.x, so we kept it enabled. Then our data will be submitted in a counterclockwise manner. I will delete the excess vertices here. 0, 1, 2, 3. Okay. Then define the vertex index. The definition is counterclockwise. Then create an index buffer object, or IBO. Then bind. Then the cache bound here is not array underscore buffer. Instead, it's a program called element underscore array underscore buffer. This is specifically used to bind index buffer objects. And you can also pass data to it. Due to the index value, there is neither a decimal point, and it's impossible to be negative. So we'll have to use uint to save. Also, pass data to it, because we are not enough in the vertices here. So I have to use uint8. If the index value is more, you can use uint16 to store, but that's the limit. Otherwise, WebGL may not support it. What about the defining the play index buffer? We can modify it drawing method. I said that I no longer use GL draw arrays, but we'll use GL draw elements. Next, look down on its parameters. The first one is a type of drawing, still a triangle. The second one is a number, and the number remains at 6. And the third one is a type of value in the buffer and the array elements. There are two types of WebGL1. One is GL unsigned byte. The support maximum index value is 255. The second one is GL unsigned underscore short. Its maximum index value is 65535. Because we use uint8, so select GL unsigned underscore byte. Of course, WebGL extensions also support more types. This depends on whether the application platform supports WebGL extensions. The last one is the data offset. Here, it's still filled at 0. Then run it and see. It seems there's an error. So the reason for the reporting, nothing new. Okay, let's look at it again. Okay, we've successfully drawn a rectangle with the index buffer object. After that, there are more points or lines or surfaces to draw. Both can be used to reuse Vertex data in this way. Let's take a look at the second knowledge point, how to change the color of the vertices. In the previous example, we gave a triangle or rectangle plots to define the fixed color in the fragment shader. This is red. If you want to dramatically modify your color during runtime, this method cannot work, so we need to dynamically set the interface. There are two ways to input. One way is of using uniform. Another is to set by extending the apex attribute. Let's take a look at uniform first. Uniform is a way to send data from the CPU directly to the shader in the GPU. But uniform and Vertex properties are a bit different. Uniform is global. This means that every uniform variable is unique in each shader program and can be accessed at any stage through arbitrary shaders in the shader program. And uniform always keeps its own values unless it's reset or updated. Next, define a color uniform on the fragment shader that is used to receive the color values we passed in. Then the GL frag color output takes the color of uColor. Then follow the Vertex shader. We also get this uniform, its index value. The get uniform location is used. It receives two parameters. The first one is our coloring program, and the second one is the name. Next, assign a value to the uniform. The interface used is gl.uniform with a suffix. It has these suffixes on the image. Different suffixes determine its number and the parameters or parameter types. Different suffixes determine its number of parameters and the parameter types. Let's look at the first one, where f represents float1 representing int ui representing unsigned int. 1, 2, 3, 4 represents the number of this parameters. For example, 4f represents a 4 float. Next, look at the second one. The second one adds a v suffix to the first one, which means that the data is passed in an array instead. The last one is the setting of the matrix, represents the need for a second order or a third order or a fourth order square. Next, we can look at the 4 floating points or floating point array to pass data. In this, I use 4 floats. So call the interface of GL uniform 4f. Then the first one is the same as the index value. Then for color components, I set it to pure blue. Then run it to see. At this time, you can see all the colors of the rectangle have become pure blue. Of course, we can also use an array form to deliver color data. Let's add a v directly on the original suffix, then change to an array. All right, you can see it here. We can make the RGB color values random numbers. This kind will give us a different color when it's running. It is also convenient for us to observe. So let's take a look. All right. This setting method is relatively compared to all the vertices in the same color. If you want different colors for different vertices, then the method will not work. So let's see the second method of setting the vertex color to extend the vertex property. WebGL can get these three color value inputs in the vertex shader. Interpolation is done based on these three values during rasterization. That is, if the color of each vertex is different in the top of the triangle, then WebGL will directly pixel interpolation in vertex A and B. So next we need to give the vertex shader to the top color value. Let's draw it according to the value we give it. Then we modify these parts. First, the vertex property should add a color input. Add the output at the same time in order to give the fragment shader. Assignments in the main function. Then in the fragment shader here, we'll comment on it from the original uniform. Then add the color that it's been assigned to using GL_frag color. Then modify the vertex data. It turns out that we only have the vertex position data. So now there's a vertex position plus a vertex color. So we don't need a position on our side. You can use our vertex data. Then add color in the background. I put the first three filled with red, green, and blue colors respectively, and the last one filled with a random color. The last one uses red plus 0.5 of green. Okay, after setting the value of the vertex, replace the original position here into the vertex data. Then in the same way, we also get the index value of the color properties. Simultaneous activation of the color attributes. Then here, next, assign a value to the color property. The first parameter is the position index, and the second is its size. Its length size is 4. The third one is the type, because we are using the same section of memory, which is float 32. So here is also use of GL float. The fourth is normalize, where it's normalized. We don't need it. The main thing is the last two. One is the stride, and one is the offset. Everyone should still remember, before there was a color attribute, there was only one vertex data, and there was a position attribute. Therefore, the location attribute data storage between the vertices is continuous. Now that the color attribute has been added to the vertex data, the parsing method will have to change. Analysis of the new vertex data. Look at this graph with the analysis of the new vertex data. Each vertex data consists of position properties and color properties, and store all floating point data for the float 32 bits. Stride knows the step size of a vertex property in bytes. The byte of the location attributes is length 2x times byte of 4, so equals 8, plus the color properties of byte length 4x bytes times 4, so that equals 16. So the stride value is 24, and the offset can be understood as the offset of the data within a step. Also calculated by bytes, the location attribute data is stored in the store, so the offset is 0, and the color is stored after the position attribute data. Therefore, the byte of the location of the attribute data occupies the byte 2 times 4 equals 8, and this is the offset of the color attribute data. So modified stride as 24 is here, and the offset is 8. Since the vertex location attribute is no longer continuous, so it strides here. It should also fill in 24. Okay, looks okay. Next, we'll commit on the original uniform part. At this point, you can see that we have successfully applied the vertex color to the rectangle, although we provided a color for every vertex. But overall, the picture can be seen between the color and the color produces a transition. There's actually the so-called fragment interpolation in the fragment shader. So select a triangle. The rasterization phase usually results in more fragments than the other specified vertices. The rasterization phase will be relative to each fragment in a triangle shape, deciding upon the location of this fragment. Then interpolate all fragment shaders according to this location. For example, a line segment is blue and green at the beginning and the end respectively. If you are running to 70% of the line segment at this time, its color input attribute will be linear combination of green and blue. More accurately said, 70% blue plus 30% green. To summarize for today about our knowledge points, the first one is about how to effectively draw multiple triangles, and the second one is how to change the colors to the vertices. And finally, we added another point. If you have certain understanding of the memory, you may have problems with the vertex data. After all, this is nothing wrong with using float values to record the position, but is color needed? After all, every component of a color is 0 to 255, and 1 byte of storage is enough. No need to use 4 bytes at all. A float can store RGBA in 4 components. Therefore, we have 2 ways to carry out some transformation modifications. 1, create a really big buffer to fit everything, or 2, add a buffer so that positions and colors don't share the same buffer. Next, we start the first method of shared buffering. This time you have to split the colors, because it is no longer able to use floating point data to save. Do you remember when we bind data, we apply for an application like a float 32 array. This represents a floating point array of 32-bit sequence of platform bytes, and the color is enough to save with uint8. Therefore, we have to let uint8 and float 32 point to the same paragraph buffer types as array buffer. Array buffer is used to represent a generic fixed length of raw to custom data buffer, and it's an array of bytes. So next, let's create a large buffer array buffer. Then give it a length. Its byte length is positions. Now we have to restore into positions and colors. Its byte length is positions.length multiplied by the number of bytes of float 32 plus the length of colors. Then we define a position buffer. It still stores float 32, but the memory buffer pointed to it at this time is the array buffer. The color is the same. Color uses uint8 as it points to the array buffer. Okay, let's start saving data. Here is the position. We also need to define an offset. This offset represents the location of a storage in the buffer. Here, I can't be I++, but I could be I plus equals 2, because we have one position data, it has two components. Then the offset here also is plus equals 3. Because the two components of the position account for two floats, then the color of each component is in the range of 0 to 255. Therefore, the four components of the colors account for one float. Then define color. Color has an offset value of 8 at the beginning because it's a 2 float. The offset here is its stride. So 8 plus 4 equals 12. Okay, then we will bind the data here. Instead of new, the array buffer is used directly. Then take the data here. It needs to be adjusted. At this point, the parsing of the vertex data has to be changed. Let's take a look. The first one, because of vertex, its stride is only 3 float. So this is 12. Offset is still constant. And here we'll use uint8, so it should be changed here to an unsigned byte. Because the value of our current data is 0 to 255, we no longer need a float. So when we finally pass here, we'll have to let it go to normalization. Stride is also 12. Offset is 8. Now let's run it and see. I can't see the effect because I didn't change the color. So we can open the console and directly see if the code has been updated. Well, yeah, the code is updated. Okay, that illustrates no problem with the writing. Next, let's look at the second way of writing. The second way of writing is actually the same as creating a vertex buffer. Just create a buffer. This buffer storage is vertex color data. I won't go into too much detail here, just a quick run through. This piece is not even needed. Here, because of the location buffer, so its storage data, or data storage, is still continuous. The color is also the same as the color buffer, so its data storage is also continuous. Next, let's check this out. Oh, the buffer is not the same. So we'll have to bind the color to its own buffer. Okay, it looks fine. Let's go ahead and run it and see. Okay, no problem. So now we have a certain understanding of the basic working principles of WebGL. Let's try to add some texture to the triangle, and we'll do that in the next video. Bye for now.